We do look a lot like a chimp or a monkey or an ape. We look more like apes than we do like, say, chickens. On the other hand, we're more like chickens than we are like worms, and we're more like worms than we are like protozoa. So there's a sort of a chain of being, if you will, there. But everything's quite different and pretty easy to tell apart. There's a fundamental similarity, DNA, for example, across the board. Bones, if you're a vertebrate, you have basically the same bones. So a monkey or an ape would have about the same number of bones with the same names as we do. So they would have a humerus, they would have a radius and ulna in their arm. We call that homology, and homology is real. But what does it mean? The evolutionists say, well, there's your evidence for evolution right there. We share these features in common. I think there's another explanation for homology, and one is it shows we have a common creator. And if homology was not real, you could learn nothing from studying, say, a laboratory mouse that you could apply to a human. Imagine if it was chaos. Every creature was completely different. We have DNA, but cats have BLR and dogs have XYZ for a genetic code. And we have blood with hemoglobin based on iron, but other creatures have blood based on copper and what have you. It would be just physiological and anatomical chaos. Nothing could be applied to anything else. I'm not even sure we could eat other creatures that were built on a totally different system. So I think that's part of the explanation. But there's another. And that is, I think, homology, the similarity that we do see, represents optimum structure and function. A good example is the arm. The first joint is a universal joint. The next joint is a hinge joint. And then the next joint is a rotational joint. And then the grippers, the hands on the end. Now, you can look at a bird, you can look at a cat, or you can look at a dog, look at a vertebrate that has limbs, and you're going to see a universal joint, a hinge joint, rotational joint, and some kind of digits. Now get on the internet and look up robotic arm. They make these things to work in hostile environments, radioactive or whatever. You have controls out here you can run. And every robotic arm you will find on the internet, whether it's a toy or a serious piece of equipment, it will have a universal joint, a hinge joint, a rotational joint, and a gripper. And without those three joints, you couldn't, for example, pick up a glass of water, move it over here, pour, bring it back, and set it down. How about that for an explanation for homology? It's optimized function. You can't improve on it. Boats tend to look like boats, and land vehicles that roll on the land tend to have wheels and look like land vehicles. And so we have this optimized design. But all of the differences are also real. Let me share some real differences between, say, apes and humans. One of the big differences, of course, is our brain. And it's not just the size. Our brain is about 3 times the size of a larger ape. But it's the way it's wired makes it completely so. The intellectual capabilities of humans simply can't be compared to that of apes or any other creature. And then many other things, too. You can look at a human skull and tell it quite easily from any ape. I think from about the age of 5 on, you can be taught how to tell apes from humans, and if you knew that, you wouldn't be tricked by too many of the ape men you'll see pictured. Humans have a vertical face. Apes have a sloping face. If this was all you knew, you could pick out the apes from the humans, and the next time you see an ape man, look for the slope of the face. If it's a ski slope, it's not human. And then our forehead is curved. An ape, the forehead is flat. Simple test. Put your hand up here, take it away. It'll be like that, see? If you put your hand up here, you take it away, it looks like that. We need to talk. We got a problem here. Now, because our forehead is curved, it has an interesting effect on our eyes. We call these the orbit of the eye, or the eye socket. And you could think of it as like 2 ice cream cones held with the big end towards you. They would look like 2 circles. That's the way an ape eye socket looks, goggle-eyed, round like this. That's because the forehead's flat. Now, if you make a curved cut across those cones, they would become oval, wouldn't they? You're kind of cutting across the ice cream cones. So our orbits are broader than they are tall, and they're cut back on the side here quite far. In an ape, the bone comes way out here. It must cut into their peripheral vision. So just looking at the forehead, you could tell an ape from a human. Humans have nasal bones that protrude. That's what your glasses are on, and if you break your nose, that's what you break, the nasal bone. We also have a nasal spine. It's a little spur underneath here. You can feel that it stops your finger. The nasal septum attaches to that. There are no apes with nasal spines. There are no apes with protruding nasal bones. They have nasal bones, but they're flat. So apes can't wear glasses, for starters. If this is all you knew, you could pick out the apes from the human just on the nasal bones. But of course, there's many other things that could be compared as well. We lock our knees when we walk. Every time our leg straightens out. Have you noticed your toe goes out about 5 degrees when you're walking, they kind of point out like this? Or if somebody has you put your feet up on a stool, they say relax, your feet are like this. That's because there's a 5-degree turn between the lower part of your leg, the tibia, and the femur. And that 5-degree turn is automatic, you don't have to think about it, and it sets a lock. So every time your leg straightens out, you have this lock that's set. And when we stand at attention, we have those locked. Now, if somebody sneaks up behind us and clips us right behind the knee, you can fall down. And that's because you're unsetting the lock. There's not an ape out there that can lock its knees. So when apes walk, they walk with a slight bend in the knee. And if you try walking that way, you'll find it's very tiresome very quickly. And even when we're walking along, every time the leg straightens out, that toe goes out a bit, and we get that lock temporarily until we bend the knee to make the next step. It's amazing how many things go on automatically just as we walk. In the medical school, we do an hour lecture on the bones, the joints, the muscles, and the nerves involved in making a single step. And if you had to think about all that, you wouldn't be able to walk. In fact, it's funny, when the medical students get up to leave that lecture, I see some of them stumbling. They're trying to think their way through. Let it go automatic. So many, many things, many details are different, and yet homology is real.